Hello and welcome to another Python tutorial. Today we are going to talk about vectorization. Now, part of the reason why we love Python is because it's dynamically typed. And this means that the type is not determined until the time of execution. And this affords advantages such as being very readable and easy to understand. But there are optimizations that can be realized by static typing, which are not realized by Python. And this is an area of optimization that we're going to learn today. What is vectorization? Vectorization is the process of transforming your data into a form in which operations can be done on the entire dataset rather than element by element. Let's take an example. So, imagine you were doing a data science project and you wanted to do a normalization of operation by subtracting the mean. This code here does exactly that. So we have a data set here, we're calling it data, and we are initializing it as a list. This is list comprehension here, a large data set of 50,000 records. We're using the random function to populate the items. This is list using the list comprehension. And then here we have something I have created called a timing constant, a timing context, which basically just times our code. The specifics of this timing context is out of the scope of this tutorial. So we have the mean here that we are getting. So the sum of all the data of divided by the length of the data. And then again using list comprehension, every data item we are subtracting the mean. And that, so if we run that, just a moment, it takes time. As you can see, it takes about 8 seconds to compute. Now, 8 seconds might seem like a short period of time, but if you remember that the attention span for humans is 7 seconds, then that's a lot of time. So what can we do? Take a moment to think about what's happening here. We have to go through each item inside of the data, and we have to do that one by one for each element, and that takes quite some time. And this is where vectorization comes in. This improvement is twofold. One is memory optimization, and two is what we call a concept called single instruction multiple data. Let me talk about memory optimization. So a Python list in the background is just a collection of pointers to objects in memory. So it doesn't really store the actual items, it stores pointers to the actual items in memory. And these items are actually objects. So for example, if we had a list of integers, it would be a list of pointers to the integer objects in memory. And each time you want to do an operation on the integers, the runtime will have to go to each individual pointer, get the integer object from memory, and then call its specific function. So for example, if you're doing an add, it would call its add function. But the thing is, computers are very good at dealing with low-level memory representations such as integers and floating point numbers. By adding that extra layer of complexity, that is having to deal with objects instead of actual integers, you create a memory inefficiency, which is why Python is becoming slow in this instance. So we'll look at how to improve on that later. Another area of optimization is the single instruction, multiple data. A single operation is able to be done on an entire data set simultaneously. It doesn't have to go through each item individually. Now, like I mentioned, Python is dynamically typed. The best way to realize the advantages I mentioned earlier is to use a statically typed language. But Python is not statically typed. So what do you do? The answer is you create a Python library using a statically typed language like C. And that is exactly what NumPy is. So let's look at an updated version of the code we had earlier. So in this case, instead of having it as a Python array, we're having it as a NumPy array. Now, because NumPy is implemented in C, behind the scenes, this NumPy array is actually is an actual C array, which means that the C compiler knows beforehand the type of data that is inside of this array. This time we're using the sum method, which will be operated on the entire data set on the NumPy array instead of the Python list. We're using the minus again. It's doing this operation on the entire data set, not a single item at a time. So let's see what happens when you run this. You see, now we have it at 0.2 of a second from 8 seconds. You see, this is a very significant gain in performance just by switching how we represent our data. So remember, memory optimization. Instead of using Python lists, which are slow, because the runtime is working with complex objects, we are using C arrays instead, and this affords us performance gains. And again, single instruction, multiple data. One operation is being done on the entire dataset as opposed to one operation at one item at a time. We're leveraging the concurrency and multiprocessing capabilities of modern computers to process this data simultaneously, and that's why you're seeing such a large jump in performance for these operations. Now there is many operations afforded by numpy arrays which you can leverage to improve your items. Let's take an example. So imagine you're writing code for a warehouse which has employees who pack boxes of four different sizes: small, medium, large, and extra large. So these employees are paid according to the number of boxes packed and the size of boxes packed, with the smaller boxes fetching lower amounts than the higher boxes. How could we represent this in Python? So in my case, I have them as four lists, each of the lists representing the small, medium, large, and extra large boxes packed by the employee respectively. So for Harry, 89 would be what he packed for small, 70 for medium, 66 for large, and then 40 for extra large. And then the same for Mary, Danny, and Tracy. And then this dictionary here represents the amount that is paid for the individual boxes. So these are the what the employees packed. This is what is paid according to the size of box. So let's say you were tasked with getting the number of boxes that were packed in a day. So how many small, how many large, how many medium, how many extra large boxes were packed in a particular day. We could go the old-fashioned way and use Python lists and loops to compute this. But knowing what we know today, we want to do that efficiently using NumPy arrays. So to do that, first of all, I need to convert the Python lists into NumPy arrays, and this is what's happening here. So how would we go about getting how many small, medium, large, extra large boxes were packed in a day? So easy. We'll just use the addition operation here. We can do that. I'll just comment out that. The array that we get there would be how many small, medium, large, and extra large boxes were packed in a specific day. NumPy does offer other aggregation functions like min, max, sum, etc. And this can be used to get the min, max, sum of items inside of the NumPy array efficiently. Let's take an example of when if you wanted to get the total number of boxes packed by Tracy, for example. That would be simple. You simply have to call np sum on the Tracy array. Also, NumPy allows us to define what we call U functions, that is universal functions. These are functions that operate on on every item on an array. So let's say, for example, we wanted to find out how much we would owe to Tracy for her day's work. How do we go about doing that? Now, obviously, there isn't an inbuilt U function that can do this, so we'd need to create our own. Let's see how we can do that. So a U function is created from a normal Python function. So we'll define a function called calculate pay, and what it does is it takes item and pay, which will be passed in from the arrays we'll pass in, and then it returns the item multiplied by the pay. And this line here is what creates a U function from a Python function, and it takes three arguments. The first one is the function we want to use as our U function, and then how many arguments does this function take, and then how many values the function returns. That's what's happening here. So how we'll go about using this function is now calling our custom U function on two arrays. Remember, it takes item and pay, so we'll need to pass two arrays, one of them containing the items and the other one containing the pays. So the first one, the one that contains the pays, is the Tracy array. Remember, this array stores the number of boxes that Tracy has packed for the day. The next array that we need to pass in is the array of payment values. For that, we're creating an array from the values of the pay dictionary. So this is the pay dictionary. We're using the dot values method to get an array of its values. So 20, 40, 80, and 160, and that will be done respective of that order. So when we print the pay per size, we expect to get how much is being paid for packing the boxes of each size. So let's run that. So this is what should be paid for small. This is what should be paid for medium, then large, then extra large, and that's what we have going on there. So we this is happening from our custom function that we created there. So how would we go about getting how much the total that we should pay her for the day? That would be super simple. We just use what we talked about. We'd use the np.sum on the pay per size array, and this will give us the sum of the items inside of that array. So if we run that now, we get 6480, and that is what we should pay her for her day's um, work. Should you therefore replace all your Python loops with this technique? The answer is no. Vectorization does come with its limitations. Let's look at some of them. The first one would be extremely high memory usage. Typically, in data science applications where you need to do large data sets, any operation that has to make a duplicate of very large data items runs a risk of running into a memory overload error. If your machine has to create a copy of a very large data item and it's already low on memory, then it's not able to do so. You need to be careful to look at the size of your data and if your machine can handle such sizes of data. It's always important to do that. One technique that I would recommend doing is modifying items in place. Let's take an example of how this might be the case. I have a data set that is of very large dimensions here, and I want to copy it into this resultant array. If I try to run that, you see I get into a problem here. My machine is not able to allocate that much storage to process my arrays. So you need to look at the memory efficiency of your code. Another limitation of this technique is that only supported operations are fast. Only operations that can happen on the elements simultaneously are fast. The moment you introduce an operation that has to happen element by element, then you negate the benefits of vectorization. For example, string operations. String operations are inherently hard to vectorize because of how strings are represented. They are actually quite hard, quite complex data structures, and they're not as easy to represent using low-level machine code. Let's look at an example. So here we have a task. We want to convert a list of lowercase string items into a list of uppercase string items. So I have a large array of strings here. So it's a string A, B, C, D, E, F, G, H, I. These three strings, and then I am doing them very many times here. I'm already converting it into a NumPy array. So I have a simple function here that converts every single item in the array into its uppercase form. That's what's happening there. Then we have another operation here that is the vectorized form of the same operation. So this one does not use the loops. Instead, it's using the vectorized way of doing the same thing. So if I were to time the two functions, that's what's happening here. I'm timing the two functions, that is the function and the vectorized string manipulation here. So I'm timing the two. And as you can see, the vectorized implementation is marginally faster than the one that uses loops. So in this case, we haven't realized that much of a difference because of vectorization, and that's because of how strings inherently are hard to vectorize. If you have a bunch of operations that are string manipulations, maybe vectorization is not the best option for you. The final limitation of vectorization is that the advantages are only realized on bulk operation. So if you have an operation that works on a list of say 10 items, then probably vectorization is not for you. The advantages are only realized if you have a data set in the millions and billions of records. You don't have enough performance gains for smaller data sets that would warrant the extra complexity in terms of readability that you introduce to your code by introducing vectorization. So in conclusion, vectorization is a very good technique that you can use to improve the performance of your code. However, you should also be careful to consider its limitations in your implementations. With that said, Thanks for watching. See you in the next one.